Hello, everyone. Welcome to Limits Involving Infinity. In order to start this lesson, the first thing that you're going to need to be able to do is draw this graph. So I'm going to draw it for you, but you should go ahead and try and do it on your own. Think about what the different asymptotes would do. Okay, I kind of gave you a minute there, but if you didn't know how to draw it, remember that there are two things that you really want to look for: the horizontal asymptote and the vertical asymptote whenever you have a rational function being something where there's a variable in the denominator. Vertical asymptotes are the easiest. Just what would make the denominator 0? So x minus 2 equal to 0 would be if x was equal to 2. So the vertical asymptote is x is equal to 2. So I'm just going to go ahead and draw a dotted line there. That's my asymptote. And the horizontal asymptote can be determined by using the coefficients of the numerator and the denominator when you have like powers. We don't have like powers, so you could use the rule of thumb that when the denominator has a greater power than the numerator, it's always going to be y is equal to 0. But if you want to see that played out, you can think of this as 0x plus 1 over 1x. 0 divided by 1 is 0. So the other asymptote is going to be right there. So I usually just plot 1 point. We're just trying to make a sketch really fast. I'm going to pick 0. When I put a 0 in, I get negative 1/2. Honestly, that's just enough for me to make an entire picture of this thing. So we briefly talked about this in the last lesson, but it will be the majority of today's lesson, which is what does it mean when we approach an asymptote? So this notation, let me just erase my asymptote information. This notation that you see here means the limit of 1 over x minus 2 as x approaches 2 from the left. That little tiny minus means from the left. So here's the left, here's the negative side, here's the plus side. So as I'm following this graph, I'm getting closer to this asymptote. I'm getting closer to the line x is equal to 2, but I'm following the graph. Remember that a limit is the expected y value. What do I expect the y value to be? I expect it to be negative infinity. It is going down. As I approach from the right, this means from the right. So I'm coming in from the right, and what am I expecting the y to do as x approaches 2? I'm expecting the y value to go to infinity. When the left-hand limit and the right-hand limit don't agree, then there is no limit. So we did talk about that briefly the other day. A much more interesting concept is this one. What does it mean for x to approach infinity? Now, infinity is not a number. You can't actually approach it. It's like a destination. You keep walking towards it, but you'll never actually reach it. So I wrote a little note here for you at the bottom. It's important that when we say as x approaches infinity, we mean as x moves increasingly far to the right on the number line. So here, x is 2, and then 4, 5, 6, 7, 8, 9, 10, and then eventually 100, and then 1,000. What is the expected y value as x gets bigger and bigger and bigger? Well, you can see that by the asymptote, the y is almost 0, but it's an asymptote. It doesn't actually touch it, which is the whole meaning of a limit. It doesn't actually reach 0. It just limits out at 0. When x approaches negative infinity, the same thing. So again, unfortunately, I'm on a different page. I'm going to make this graph super quick. But now x approaches negative infinity means I'm moving to the left and I'm following the graph. And what do I expect the y value to be? Again, it's going to 0. It just keeps getting smaller and smaller and smaller until it's almost 0. Okay, so that's a rational function. Of course, not all functions are rational. So let's look at x going to infinity for other functions. X cubed, number 1. 0, 0, 1, 1, -1, -1. Remember, hopefully all those pre-calculus graphs are going to come back to you. We're going to do them super fast. So now, this one goes up so fast, you don't even think about this going anywhere as x goes to infinity. But if you had x is 10, what is the y value? It's 10 cubed. It's way up there. And as x is a million, it's a million cubed. What happens to the y value? It just gets infinitely large. So the limit as x goes to infinity, the y is also going to infinity. Now I could change this graph a little bit. For number 2, x cubed plus 2x plus 1, I don't really know what that looks like. But let's just say it did that. We know that it has the same general behavior as x cubed. It still goes up in the end. All that you really care about is the x cubed. So you don't even need to be able to graph that accurately. Once you see the x cubed, you know what the end behavior is going to do. For the next one, number 3, again, I don't know what that looks like. I mean, I know that it crosses at -2, but in the end, I know that it's going to go up. But this one, notice, is asking for x goes to -infinity. So as I move in this direction, what is the y value doing? It's going down, so -infinity. Now, number 4 is a little different. I am going to have to redraw this one because it's a negative x cubed. So it goes like that. General shape is all you need. And as x goes to -infinity, which means as it goes towards the left without bound, what is the y doing? The y is going up to +infinity. This is an important example because I know this is going to sound dumb, but when I was in high school, I'm sure that my teacher did a good job explaining it, but I was just looking for a pattern. I was like, oh, look at that, infinity, 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 and then -infinity, -infinity. I'm not sure that I completely understood the concept at the time, but I felt like I had a pattern down. But you can see that's not always the answer, so be aware of that. As x goes to -infinity, in this case, the answer is +infinity. So there's going to be rational functions that don't have nice, easy asymptotes that you can graph. I don't even know what the vertical asymptotes are for this one. But there's a really cool algebraic way to do this problem. What we're going to do, it's like a trick. We're going to divide through by the highest degree of x in the denominator. That's what I've written here. So I'll show you. Don't forget proper notation. I'm going to rewrite the word limit in order to keep it equal. So 7x cubed divided by x cubed. So I'm dividing each term by x cubed. X cubed over x cubed minus 3x squared over x cubed plus 6x over x cubed. And that gives me, be aware of your notation, x goes to infinity. The top becomes 7, and the bottom becomes 1 minus 3 over x plus 6 over x squared. So we're going to bring back an old lesson for a minute. You may remember the properties of limits said you could do pieces of things. So you don't have to be able to do this limit as a whole. You could do the limit of 7 and the limit of 1 and the limit of 3 over x and 6 over x squared and see what you get. Just do them all in pieces. So since this is a new lesson, I'm just going to remind you that this is really the equation y is equal to 7. We're finding the limit of the equation y is equal to 7 as x approaches infinity. Well, as x approaches infinity, the y value is still going to be 7. So the answer to this would be 7. And same thing for this one. When y is equal to 1, even if you go all the way out to infinity, it's still going to be equal to 1. But think about this graph. This graph is 3 over x. It has a vertical asymptote at 0, a horizontal asymptote at 0. It's negative, so if you plugged in a 1, you'd get -3. So it looks something like this. But as x approaches infinity, what is the y value becoming? 0. Now, you're not going to actually make all these graphs. I'm really just during the lesson trying to help you understand how that works. But as a shortcut, this is how I usually think about it without actually making the graph. I think to myself, if I had $6 and I divided by infinity squared, pretty much everybody's going to get 0. $6 divided by infinitely squared people. So if you don't want to think about it graphically, then just think about it in a common sense way. So this becomes 7. That is the answer to the limit of this function, which you can't possibly graph easily. But now at least you know that in the end, it's going to limit out at 7. If you would like to stop the video and try the next one on your own, you can. But I'm going to keep going. It's always good for you to pause. You know if you were in class, I would make you do it on your own. But we don't have that luxury. So I'm going to keep going. Divide through by the highest power of x in the denominator. X squared over x squared minus 5 over x squared. Notice I keep using proper notation. Limit. I get 1 over x plus 2 over x squared. 1 minus 5 over x squared. And again, I would love for you to be thinking about this graph, but even if you don't think about the graph, the quick way to do it would be to say 1 divided by 1,000,000 people is nothing. $2 divided by 1,000,000 people squared, they each get nothing. The limit of 1 as you approach 1, we already did that, as you approach infinity is just 1. It stays at 1 forever. And then $5 divided by infinitely squared people, 0. 0 over 1 is 0. So if you really can't stand graphing, this method works. It only works for the limit as x approaches infinity. This is not to be used if the limit approaches 3 or 8. It's only for the limit approaches infinity this method works. Now, here's the interesting thing. Actually, let me just get rid of it all. You can always go back to it if you need to. Here's the really cool thing. I want you to think about what asymptote means the same thing as a limit. Even though it would be challenging to find the vertical asymptotes, you know there's 3 of them because of the x cubed, you do know the horizontal asymptote. The powers are already the same, so it would be 7 over 1. 1, 2, 3, 4, 5, 6, 7. This asymptote is where the graph is going to end up. I realize it has a bunch of vertical asymptotes. I don't know where they are. I'm totally making this up. So maybe the graph goes like this. I have no idea what the graph does, but I do know that in the end, it follows this asymptote. So I could have told you the limit was 7 without doing all that other work. So if you're good at asymptotes, then it's finally all going to pay off. Same thing with this one. What is the horizontal asymptote of this one? 0x squared over 1x squared is 0. The horizontal asymptote and the limit are, as you go into infinity, are going to be the same thing. This one, I can figure out the vertical asymptotes pretty easily. X squared is equal to 5. X is equal to plus or minus the square root of 5. So 2 point something. But even if I don't know what the graph looks like, I know it has a horizontal asymptote at 0. So maybe this is like this, or maybe it's like this. It doesn't really matter. In the end, this graph is going to go to 0. Look how much faster we just got those 2 answers. And on this next page, I sum this up for you. here under horizontal asymptotes. If the limit as x approaches infinity is equal to b, or if the limit as you approach negative infinity is equal to b, then the line y is equal to b is the horizontal asymptote. And vice versa. If you know the horizontal asymptote, then you know the limit as x approaches infinity. So literally, all you have to do is think about the horizontal asymptote of this graph, and you've got yourself an answer. For number 2, horizontal asymptote of this graph is 2, so the limit is 2. If that's the horizontal asymptote, no matter what the vertical asymptote is, you know in the end it's going to limit out at 2. Now this one has, this is the example from before, by the way, so that should be answers on the other page. This one has an oblique asymptote. But again, can you picture what that means as you're going to infinity? It means somehow, in addition to a vertical asymptote at -2, somehow it's got something going up here. I don't know exactly where it is. It could be there, it could be here. I don't care where it is. All I know is that this graph, whether it looks like this or whether it looks like this, I don't know what it looks like. But can you see what it's doing with the expected y value? As x gets bigger and bigger and bigger, as x goes to infinity, y is also going to infinity. Unless the graph was down, but then you would have a negative here. That's what would control the graph ending up or ending down. But it doesn't have that, so we'll delete that. All right, I'm going to go back a page because we went straight to horizontal asymptotes. I did skip over vertical asymptotes. We did this right at the beginning of this lesson. As you approach a vertical asymptote, there's really only 2 things that can happen. So on this one, the vertical asymptote is at 3. Horizontal asymptote is at 0. This equation looks like this. So as you're approaching from the right, the limit as x approaches 3 from the right is going to be infinity. The limit as x approaches 3 from the left is going to be negative infinity. So it's coming in from the left and it's going to go down to negative infinity. So to just say the limit as x approaches 3, there is no limit because the 2 limits don't match. So vertical asymptotes and horizontal asymptotes that you learned in pre-calc are huge in calculus because they help us understand limits. All right, I'm going to give you just a minute to do this. You should literally be able to do it super fast. And I'll fill in the answers in just a minute. If you're not ready for answers, go ahead and hit pause, but I know some of you are that fast. Oblique asymptote, so it's infinity. Oblique asymptote, but we're going to negative infinity, negative infinity. Asymptote is 0. Oh no, they're both x. 1/7, 1/7. This asymptote is 0, so it doesn't matter if you're going to positive or negative infinity. This asymptote is oblique, but we're going to negative infinity, so we're going down. This is 2/3, and this one is 0. You literally should be able to do them just that fast. So we talked about this sine of x over x last class. The graph for sine of x over x looks something like this. I think I told you that I really wanted you to memorize the graph instead of the information, and now you know why. Because you're going to have to memorize both sine of x over x as x approaches infinity and sine of x over x as x approaches 0. And you don't want to get them backwards. But if you have the picture, then it's pretty obvious that as you're approaching infinity or negative infinity, you get 0. And the one that we did the other day was the limit as x approaches 0 is going to be 1. So that was a graph that we did before. We didn't do the cosine graph when we were going to 0 because it doesn't exist. So the cosine graph kind of goes like this, and then it goes down. And then on this side, same thing, it kind of goes like that. And then that's not exactly right, but it's close enough to get the idea that from the right, it goes to positive infinity. From the left, it goes to negative infinity. But in both cases, as you go to infinity, the limit is 0. So there's this cool theorem called the Squeeze Theorem. It was actually cooler when I was growing up. They called it the Sandwich Theorem because you were finding the inside of a sandwich. So I'm going to show it to you. It's pretty neat, pretty easy. So hopefully you would agree that sine is always a value between 1 and negative 1. Sine goes up to 1, down to negative 1, up to 1, down to negative 1. That's sine. So what I'm going to do is I'm going to divide each part by x, because that will give me the equation I'm actually looking for, sine of x over x. I am going to throw in there that x is greater than or equal to, not greater than or equal to, just greater than 0, because a negative would reverse everything. And then, remember, whatever you do to one side of the equation, you do to the other. In this case, whatever you do to one part, you do to all 3 parts. And then I'm going to add the word limit. Okay, so now I have the format that I want. So let's fill in this limit. Negative 1 over x is this graph right here. And as x goes to infinity, what is this function doing? The expected y value is 0. And then on the other side, this graph, oh, I wrote this wrong. 1 over x. 1 over x looks like this. And again, as x goes to infinity, then this also goes to 0. So they call this the squeeze theorem because if the limit we're actually looking for is some number between 0 and 0, then therefore this 3 dot symbol means therefore the limit as x approaches infinity of sine of x over x is equal to 0 by the squeeze theorem. That's all it says. In simplest terms, you know the numerator is always between negative 1 and 1, so it's kind of like a constant. And then as x approaches infinity, the function c over x becomes nearly 0, if that's an easier way for you to think about it. Okay. Now, how do we actually use these? Let's do some examples. So in example number 1, we are going to break this limit down into 2 separate functions, 5 of x over x plus sine of x over x. Technically, you need parentheses to show that you're taking the limit of the whole thing. This simplifies to 5. Remember that that means you're finding the limit of the equation y is equal to 5, which is just a horizontal line. And what is the expected y value when you get it way out here at infinity? I expect it to still be at 5. And what do I expect y is equal to sine of x over x to be? Way out at infinity? I expect it to be 0. And so the answer is 5. On number 2, I love number 2. This is one, only because I'm a little mean, sorry. Because I would let you guys try this for at least 2 minutes. And sorry, except for the very brightest of you. No one usually gets it. But I'm not going to sit here and just let my video run for 5 minutes while I try and let you get stumped. You would just fast forward anyway. So the key to this one is using that trick that I just taught you a few minutes ago, dividing through. So it does have other uses. It's something to keep in mind. And what it did for you in this case is 2 things. Number 1, it gave you the format sine of x over x. The reason that's so important is because just sine of x doesn't have a limit. Think about it. Y is equal to sine of x goes up to 1, down to -1, up to 1, down to -1. As it goes to infinity, I don't expect anything to happen except that it keeps oscillating between +1 and -1, where sine of x over x does have a limit. It does become 0. Cosine of x over x also becomes 0. And since this simplifies to 1, the equation y is equal to 1, I expect that to stay at 1 as x goes to infinity. And since this becomes 1, also 1. Now, there's probably somebody in the class that did pause their video, good job, and said, oh, I got that. Anyway, I just said that the powers were the same. But that power trick only works for polynomial functions. Trig changes everything. So if you did it that way and you got 1, you got lucky. Don't count on it happening again in the future. And then number 3 is on here just as a reminder that the 2 is a constant. You can think of this as 1/2 times sine of x over x, where again, this is 2 limits being multiplied by each other, and you can do their limits one at a time. You might remember that we did limits approaching infinity, we did limits, properties of limits where things were being multiplied. So this limit is 1/2, and then this limit is 0. So the entire answer is 0. All right. So just to wrap things up, we have a little shortcut guide. You can read that on your own. I'm not just going to read things aloud to you. I know these videos are already a little bit long. But pretty much in short, the rules that you learned for finding the value of a horizontal asymptote now can be applied to finding the limit as x approaches infinity. How fast should you be able to do 1, 2, and 3? Literally so fast. If it's oblique, the only thing you need to know is if it's ending up with its oblique asymptote or if it's ending down. Since this is a +3 over a +1, it's ending up, so positive infinity. This one, the numerator has a power less than the power of the denominator, so it's 0. These powers are the same, so it's 2/3. It's a beautiful thing. Have a great day.